So let's say that Newton's exploring and he comes upon a hill, and in honor of Harold, we'll make it a purple hill, and the hill looks like this. Newton notices that the hill is smooth on this side and really steep over here, so he has to go up. It requires a lot of force to get up that side, but over here it wouldn't be much force to hike up that side. Maybe he walks around it and decides to go up this way. But hills are graphs. Hills are actually graphs, because you could take a photograph of them, y versus x, right? But hills are graphs of gravitational potential. I guess my point is that this hill is a graph of height versus x. And if I wanted gravitational potential, I could take, well, I know that gravitational potential has to be equal to gravitational potential energy divided by, oh, what is it? Gosh, is it divided by mass? Yeah, I suppose it is. And this is mgh, and then I'm supposed to divide by mass. In a uniform field, it's mgh. Divide by mass, so the masses cancel. So gravitational potential energy is simply g times h. Not gravitational potential energy. Sorry, gravitational potential is just g times h. So I could rescale this by multiplying by g, and nobody would notice. So a hill is a graph of gravitational potential. And that's all well and good for gravitational things, because that means it's also a graph of gravitational potential energy for all mass, because I multiply by m and I've still got the same shape. But if an electricity, now our electrical analogy says that V electrical is equal to, well, it's equal to negative ed, but if I multiply by charge, then I'll get energy, and the problem is that multiplying by charge gets me this relationship right here, and this could change completely if the charge is negative. And that's why it's so important to study electrical potential, because it's independent of charge, and you can draw a graph of electrical potential and then think about how the energy would work based on which charge you have. Okay, so if you believe that hills are graphs of gravitational potential energy, hills are graphs of gravitational potential in this case, then I could show you a topographical map for this same hill. Let's say that Newton comes and he does some surveying, and he finds that this hill has a particular graph that looks like this. And you see, because of the density of the lines right here, we've got, well, what are these things called? Topographical lines? What do you want to call them? I want to call them lines of equal height. Altitude, I guess you could call it, but we've been talking about the word h meaning height for a long time. So these suckers right here are lines of equal height, or we could even, we want to be fancy, we could call them equi-heights. If you want to be even fancier, you could call them equipotentials. We're going to do the exact same thing with our we're going to do the exact same thing with electricity. And you've already seen a graph of an electrical hill very much like this, and we could make a topographical map from it. I'll show you how that works. The electrical hills that we recently discussed was, what did we have here? We had potential as a function of location, and we had one line that went up like this. And we had another line that went down like this. I don't remember which one was on which side, but I don't really care very much. Notice at this point, the potential is exactly 0. This must have been a charge right here. What did we have? Q1 right here. I don't even care. We had a Q2 right here. Q2 seems to be negative, and Q1 seems to be positive because its potential is infinite, and this one's potential is negative infinite. Now, what I'm about to do is show you that we can make little circles on this sucker that represent every particular height, like this height, that height, that height, that height. Let's make a circle at each one of those. This one, that one, that one, that one. And you kind of notice that they're getting, and then the next height, next circle has to be all the way down here. This one will go doot, 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 like that. And we'll get a circle here, and a circle here, and a circle here. And a circle here. And you notice that the size of the circles begins changing less as we go further and further down here. And that's a very interesting pattern. Maybe I should try looking at a top view or a topographical map of this potential versus location. And in that case, I'll be able to see also the direction that's into the page and out of the page. And we expect symmetry between this direction and that direction for a point charge. But I guess I'll draw it over here and see what we get. Now I'm going to make a topographical map of the potential. I'm going to put a charge here, this will be Q1, and another charge here, this will be Q2, and we notice these blue lines have to be incredibly stacked up on here, like billions of them, and then they begin spreading out more and more and more over here. And these guys are also going to have the same pattern, except this one, you're looking down into a pit. Can you tell that you're looking down into a pit here? Not from a simple topographical map. Somebody would have to tell you that this is a down hole, and this, well, this sucker here is a huge mountain. Okay, and this is a huge pit of despair. And then there's level ground. Let's see if I could draw myself a purple line where the ground is level. Right here, right in between the huge mountain and the huge hole, there must be level ground. Level ground sounds like equi-height or equipotential. So this sucker right here is equipotential. Where else could I find equipotential? How about, wait a second, this line right here. This is equipotential. Yeah, everywhere around here, this is flat ground, so it's an equipotential. All right, so here's the thing. A force on a charge would point, let's say I put a charge right here. It's a positive charge. Charge feels force. Which way? Downhill. It's just like a rock, right? If it's a positive charge feels force downhill. And the cool thing about a negative charge is just by virtue of this minus sign here for the charge, if the charge is negative, then the charge will feel a force uphill. That's the same thing as saying that negative charges want to go closer to positive charges and negative charges want to go away from negative charges. So if I put a negative charge right here, I guess I'll go black for that. Put a negative charge right here, that sucker will feel a force that direction. And if I put a negative charge right here, that sucker will feel a force that direction. But if I put a positive charge, where? Put a positive charge right here, that sucker will feel a force that direction. It will want to go downhill. Similarly over here, now, let me be a little bit more careful. If I put a positive charge right here, it wants to go downhill, and this is a huge mountain, so the positive charge will feel a force that direction. And if there's a positive charge right here, then it will feel a force, well, it wants to go down the mountain also, and down the mountain is this direction for that positive charge. If I put a positive charge right here, it would feel a force exactly that direction. That's the direction right down the hole. I took a math class at college that, well, it was Math 501. It was co-listed with physics. It was mathematical methods, and we learned the method of steepest descents. And so the steepest way to get down this hill, if you happen to be right here, is exactly normal to these lines of equipotential. It turns out that being normal to a line of equipotential is a very, very important thing. That's the way to most rapidly decrease your energy. This is why rocks roll downhill. They're trying to save the universe energy. So the cool thing about these forces that would be felt by a small positive test charge is the direction of the force felt by the small positive test charge defines the direction of the electric field. So these vectors are, in fact, electric field vectors. And electric field vectors are always normal to equipotentials. That's worth writing down. And I have to put an L in to spell a word. Good work. Electric field is always normal to equipotentials. Okay, wait a second, what if I put a charge right here? Would it go that direction? Sure, and a charge right here would go that direction, and a positive charge right here would go that direction, a positive charge right here would go that direction. Are we drawing the electric field of a point charge here based on our graph of equipotentials? Ding, and right here it would go that direction, and right here it would go that direction. And if I connect these lines, then we find the electric field lines we've studied a week ago. And notice how the electric field lines are always normal to the lines of equipotential. Here's a line of equipotential, and every electric field line is going to be going that direction. And they go in the direction of decreasing potential. And the way to fastest decrease your potential is to go directly normal to an equipotential line. That is to say, if you want to roll down a hill, go straight down, not diagonal down. It's the fastest way to get down the hill. Also, we should study, instead of just point charges, we should study equipotentials in a parallel plate capacitor, because that's going to be even easier. So I'll make you a blue parallel plate capacitor. How am I doing centered-wise? Oh, that's pretty good. All right, here's your parallel plate capacitor. And, well, I'll get myself a little bit more room in here. And I'm going to put some positive charges on one side and some negatives on the other. And if I set them up like this, if I set these suckers up like this, where is the high potential? This is the high potential here. And the low potential is over here. And you know that lines of equipotential, ooh, what did we say about lines of equipotential? Lines of equipotential means that the potential is not changing. And I guess in the case of a hill, a line of equipotential for a hill was a line of equal height, which means that the energy of a charge would not change as long as you move along an equipotential. I think I reserved that pleasant color baby blue. Oh shoot, I got baby blue all over here. Baby blue is representing my lines of equipotential. So I'm going to put some lines of equipotential here, and then I think I'll define some voltages for us so we can make this a little bit more concrete. I'm going to say that low voltage is 0, and I'm just going to go crazy here, and I'm going to call this line a potential of 10 volts, and this one will be 20 volts, and this guy will be 30 volts, and this guy is going to be 40 volts, this guy is going to be 50 volts, and then this plate has to be 60 volts, the way I've stacked it up right there. So interestingly, the line that's directly in the center is halfway between the voltage of the high plate and the voltage of the low plate. Now you know my decision here is arbitrary to make that 0 volts. I could make that potential negative 60 volts. In that case, what would be the potential of the V high? You can figure that out. That's another way of looking at the same problem because it's an arbitrary decision who gets to be 0. So yeah, okay, maybe that's too much of a clue. Meanwhile, if the lines of equipotential are vertical here, and I guess extending into the page as well, then I need electric field lines that go normal to these lines right here. So I'm going to be probably doing something like that. Those are my electric field lines. And that's why I have a uniform electric field, because it will be normal to my planes of equipotential. You could imagine slices of paper. These paper lines are the lines of equipotential that are right there. All right, good. So we got right angles right there. We said some stuff about electric fields. I revisited the field as a right. Yep, good. Goodbye. Versus X. And if I wanted gravitational potential, I could take, well, I know that gravitational potential has to be equal to gravitational potential energy divided by, oh, what is it? Gosh, is it divided by mass? Yeah, I suppose it is. And this is mgh, and then I'm supposed to divide by mass. In a uniform field, it's mgh. Divide by mass, so the masses cancel. So our graphs, hills are actually graphs, because you could take a photograph of them, y versus x, right? But hills are graphs of gravitational potential. I guess my point is that this hill is a graph of height multiply by m, and I've still got the same shape. But if an electricity, now our electrical analogy says that V electrical is equal to, well, it's equal to negative ed, but if I multiply by charge, then I'll get energy, and the problem is that multiplying by charge gets me this relationship right here, and this could change completely if the charge is negative. And that's why it's so gravitational potential energy is simply G times H. Not gravitational potential energy, sorry, gravitational potential is just G times H. So I could rescale this by multiplying by G and nobody would notice. So a hill is a graph of gravitational potential. And that's all well and good for gravitational things because that means it's also a graph of gravitational potential energy for all mass because I'm. So let's say that Newton's exploring and he comes upon a hill, and in honor of Harold, we'll make it a purple hill, and the hill looks like this. Newton notices that the hill is smooth on this side and really steep over here, so he has to go up. It requires a lot of force to get up that side, but over here, it wouldn't be much force to hike up that side. Maybe he walks around it and decides to go up this way. But hills